Test, test. Can you guys hear me? Hello? Can you guys hear me? Okay, perfect. Okay, so let's give it one more minute and then we can get started. All right, it's 7:05, so let's get started. So welcome, guys. Welcome to our bootcamp. This is a open course. So actually, I come from the Alex Ivy School. We are an organization which focuses on providing trainings and coachings for various North American math competition courses, including but not limits to, the AMC series, the Waterloo series, so on and so forth. So we're trying to provide more systematic and comprehensive trainings for various math competitions. And today we're going to focus on the 2025 Euclid Math Competition. Okay, so before we get started, we just want to give you a very high level introduction about how our lecture works. So this lecture actually contains 10 different sub-lectures. We're going to be able to cover the most important concepts, areas in the Euclid Math Competition. Generally speaking, when we are talking about the North American Math Competition, we cover four major areas: geometry, algebra, counting probabilities, and also the number theory, right? These are the four major topics, pretty much quite aligned with your like your at school courses, so on and so forth. So basically, we break our 10 lectures to follow the same criteria. As you can see here, in the first three lectures, we're going to talk about all the geometries. Today, we're going to start with the 2D geometry, focus on the triangles, quadrilaterals, polygons, so on and so forth, and followed by the next two lectures. One is going to be focused on the circles and the 3D geometry, or we say the solid geometry. And the other one is going to focus on the coordinate geometry. Coordinate geometry can be considered as a liaison between the pure geometry and the pure algebra, right? Coordinate geometry is trying to use the algebra way, try to solve the geometry problem, right? This is where coordinate geometry come from. So we can take it as a transition course to wrap up all the geometry and move slowly to the algebra part. Okay? From our lecture number 4 to lecture number 7, it's going to be 4 sessions, 4 lectures talking about the algebra. Algebra is actually all over the places. We learn algebra from day one. Everyone, you guys went to your elementary school or like even to like the kindergartens, you start by counting numbers, right? This is like 1 plus 1 equals to 2. These are the basic for the algebra. Algebra is where this entire math, that the mathematics came from. So we're going to try to cover the most important concepts. Let's say the exponential logarithm functions. We're going to talk some functions, advanced functions, some polynomials. We're going to talk something about the geometry, like the trigonometry, and also the sequence and series. These are the most important topics that you will see, definitely you will see every year in the Euclid math competition. And then moving forward, lecture number 8, we're going to go for the combinatorics, or we say the counting probabilities. So this is actually a very important session. I find a lot of students find it very challenging for some complicated, counting and probability problems. We're trying to give you guys more summary. So the focus of our lecture is not to really go through all the problems one after another. You can actually went to the, there are like so many websites or even the YouTube videos, they can cover all the problems. So our lecture is try to give you more summary, try to give you more kind of like high level summary conclusion, how to do problems. We try to classify the problems in different categories and then give you a bit kind of like a representative for each of this category. And moving forward, we're going to show you guys how to use the technology to solve the problems rather than just like repeating the solution one after another. So fish and fishing, we're definitely going to focus on the fishing part. Okay. And the lecture number 9, we're going to go to our last session, which is the number theory. Number theory is actually a very important session. And there are a lot of technologies we do not learn it very often in your day school. So we're trying to introduce some high-level theorems, like technologies, which is going to help you to solve the number theory related problems. Okay. And also we're going to use one lecture, lecture number 10, to do a question number 10 bootcamp. So basically, we're going to focus to give you guys as many as possible, like the question number 10, to give you guys, more complicated problems, introduce some high-level thinking strategies, try to solve the problem. So this is basically where we come from for these 10 lectures. And just like I said, our lecture, normally speaking, we try to break it into three major categories or three major steps. Step number one, we always start a session or like a lecture by the basic concepts. We try to summarize the most important concepts in this part and try to give you guys a more kind of like a recap about the important technologies or some theories that you have to know in order to cover this part whenever you go to the math competition. Step number two, after we get all the concept cleared out, we're going to trying to summarize different types of questions. You can have a million problem, right? A million questions, but you need to classify them into different categories. And later, especially in today's lecture, you'll be able to find out there are a lot of similarities for different types of problems. And for the same type of problem, if you want to do a comparison between American and Canadian math competition, let's say American, you have the AMC, AMC series, or the Canadian, you have the Waterloo series, so on and so forth, you'll be able to find out there's a huge similarity between the problems. Sometimes they just copy the problem from one exam to the other. Sometimes they don't even change the graph too much. So that being said, why it is important that we need to classify them into different categories rather than you just basically, brute force the problem one after another, one after another. This is going to take forever, right? But if you do some classification and try to abstract some high level kind of like strategies based on some representatives, so this is going to make your preparation process more efficient. And then step number three, after we do all the type of classifications, we're going to give some real problems. And most importantly, in all these real problems, we're going to teach you the strategy, how to do the problems, and also some conditional reactions. You know, if you go to like a math competition, you see a new problem, right? If you try to solve the problem, process the thinking every single problem, most likely you don't really have time. Especially, if you go to AMC, you only have like 75 minutes. You have to do so many problems, right? So that being said, what we're trying to do is try to give you more conditional reactions. As long as you see a certain condition, you're going to do a certain reaction. So this will make it very conditional. So there's no need for you to think, to do some like derivation, so on and so forth, but make it more like a very natural conditional reaction. As long as you see this, you're going to do this. As long as you see that, you're going to see that. So this want to make the entire process very, very smooth and very faster. Okay? So yeah, generally speaking, I like to do a very quick warm up before we get started, jump to the real problems. So this is kind of like the way how we organize our lectures to make it more, what should I say, more helpful rather than just going through the problems one after another. Summary and then give you the high level guidance is actually where we come from for this entire lecture. Okay. And one more thing is that we really appreciate and we really value this interaction by different students. So in our lecture, interaction is very important. So I know this is like open course. We have like more students, but it's okay. If you have any questions, you can either type into the group chat or you can just unmute yourself and then just basically shoot me the question. So I really like to see what you think. And from time to time, I'll be asking you guys, how to do this problem. What do you think for the next step? So on and so forth. So I always believe that learning should be a dialogue. This is not like a monologue, unidirection thing. You need to let me know what you think. Read the question, challenge me, and I will do the same thing to you. This is going to make this more dynamic for our entire structures. All right, so far, so good. Okay, if all good, let's go to our lecture number 1. We're going to go to our first lecture, which is 2D geometry. So this time we're going to focus on the triangle, quadrilateral, polygon, stuff like that. We're going to save all the circle part to the next lecture because there's so many things for the circle. We just want to make sure we focus on the topics one after another. Okay, so our first part is our step number 1 is try to do some concept summary. Okay, concept summary. Most of them are super easy for you guys, but I just want to take this opportunity to summarize them as much as possible to make sure you know what are the tools, what are the technologies that you have to fill, that you have to be equipped, right, before you go to the math competition. Well, the first one is triangle inequality. So this is actually something so easy, right? In the triangle, you make sure that what? The sum of every two sides will be greater than the third one, right? But basically, you have like three different sizes, you have three different combinations. So can we make this easier? Let's say if I ask you just try to use one, summarize them into one inequality, how can I do this? Who can tell me? Instead of writing three different inequalities, can I just basically consolidate into one inequality and cover all of them? Does anyone knows that? No? Okay, no problem. Actually, what you can do is that you can try to make sure the sum of two small side is greater than the longest side. Is it right? If you can make sure two small side, adding them together is greater than the longest one, then you automatically cover all those three scenarios. This is something so easy, right? Okay, this is one inequality that you have to know. I think there's another very important inequality in the triangle. In triangle, any kind of triangle, regardless what kind of triangle, you have two very important inequalities. One is this triangle inequality. The other one is what? Have you? So these are all the conditional react. As long as the question asks you to do some inequality stuff within the triangle, you should automatically think of all those important concepts without having to do a big search. The second one is also important is in a triangle, you have your theta is always from 0 to 180. So aka your sine theta, your cosine theta, they're basically go for such a range. Is it right? Sine theta and cosine theta. This is actually a very important inequality as well. So trust me, sometimes you can use this so easy inequalities that's going to help you to solve a lot of complicated problems. We're going to see. So we're going to show you sometimes it's going to make your life so easy to expedite your entire stuff. Okay. The second part that you need to know is the Pythagorean theorem. Yeah, Pythagorean theorem is something you learn from your elementary school. So we don't have to say too much, right? A right triangle, the two legs, and also the hypotenuse. But this part in the math competition, most of the time, they want to test you the other way around. That being said means sometimes the question give you a triangle with the three sizes, and you have to recognize this is actually a right triangle. Okay, the question won't really tell you this is a right triangle, but you have to figure out by the three sizes, or we can say the Pythagorean triples, you'll be able to recognize this is actually a right triangle. And sometimes it's more like this. The question give you some sizes. For instance, I just give an example, something, right? So basically, maybe the question give you something. You have this guy, you have this guy. And then during the calculation process, you calculate the length of the green one, and you calculate the length of the yellow one. And then you have to recognize this is actually a right triangle after your calculation. So what I'm trying to say is that sometimes the question does not really give you the three sizes of a triangle right away, but you have to do some calculation. And during the calculation process, you realize, okay, this is actually a right triangle. A lot of like the AMC problem like to give you some trick like this. So try to remember, you have to remember, at least be familiar with some very common Pythagorean triples. So these are the most common Pythagorean triples. I think the first row you need to remember because these problems actually you see them from time to time, AMC or even like Euclid. They just basically have you do some calculation and happen to find out this is actually a right triangle. Okay, try to remember this. This is going to be very important. Okay, moving forward, we'll see the very important twin brothers. One is the congruent triangle, one is the similar triangle, right? These are considered to be the foundation of the entire 2D geometry. And you're probably going to learn, you have already learned so many rules, right? So many experience for these two. So try to remember the rules, how to determine two triangles that are congruent or similar to each other. Or you need to know the properties of two triangles if they're congruent or if they're similar. Okay, I'm pretty sure you guys should knowing this pretty well, so we don't want to spend too much time. Generally speaking, the congruent triangle are basically two triangles that are exactly the same. The sizes are the same, the angles are the same. So how many ways you can do the determination? Three sizes, two sizes, and their included angle, two angles, and one of the opposite, like the opposite side of one of the angle, two angle and their included size, right? And especially for the right triangle, one left and one hypotenuse, right? Well, there's only one thing I want to mention is here, SSA, two sizes and one of the opposite angle of the one side. This will not guarantee a congruent triangle, right? I think you guys already know that in your day school, because let's say we have these two triangles here, right? They have, let's say, this is black, they are the same. Let's say this angle is 30 degrees, right? However, what about this guy? This is 6. However, I can make two triangles as the 6 as one of their side, right? So of course, this guy will be the same, right? Like the blue one will be definitely the same as the one on the left. However, you still have another obtuse triangle. So this obtuse triangle also have two sizes, number 6, number 11, and also 30 degrees. They're pretty much the same. And that's the reason why you use the SSA is not always guaranteed. I'm not saying this is SSA is completely wrong, because you can see that for the first one, this is indeed a congruent triangle with the previous one, right? But it just generates another possibility for the obtuse triangle. So that being said, in the future, if you can guarantee your triangle is the same, like obtuse or like the acute, you can still use this rule to determine these two triangles that are congruent to each other. However, most of the time, you do not have this information to guarantee these two triangles that are exactly both acute or both obtuse or one or another. So that's the reason why you cannot really use this rule. So what I'm trying to say is that many teachers say this rule is completely wrong. No, this is not completely wrong. It is still correct, but it might give you an kind of like an invalid candidate. But as long as you can screen out this invalid candidate, this is also a valid rule for you to determine two triangles that are congruent to each other. You guys follow me? Okay, you can give me a signal in the group chat, or you can just talk to me, unmute yourself. So definitely, we like to have more interactions with you guys. Okay. So yeah, just one more thing before we move forward. You can find out within all those rules, determination rules for different triangles that are congruent to each other, there's a very important thing is that at least you need to have a side information, right? To determine two triangles that are congruent to each other, at least you need to have one side. You can have two sides, you can have three sides, but at least one side. Okay. After we get the congruency, the next step is going to be the similarity, right? Similarity is actually a very important thing for the entire triangle sections. So how to determine two triangles that are similar to each other? I think you guys already know that. So you have the AA, as long as you have two angles because you only have three angles. The third one will be automatically the same. Or two sizes and their included angle. Or just three sizes. Is that right? So that being said, you actually have more ways to kind of like uh, identify two triangles that are congruent or, I mean, they're similar to each other compared to congruent. Why? People say, no, no, no. Now you previously have one, two, three, four, five. Now you only have three. Why I only have three? Because let's say your AAS, your ASA, as long as you have two A's, you don't even care about S, right? So even though it's actually lesser, one, two, three here, but actually it offers more flexibilities to determine two triangles that are similar to each other. Do you guys follow me? Similarity is actually more ways to determine rather than congruency. And two triangles that are similar to each other, of course, the properties will be all their sizes will be proportional to each other, and also the corresponding angles that are the same, right? I think you guys know that. And there's a very, very important part that most of the time you do not really pay attention to is if two triangles, they're similar to each other, the area ratio will be the similarity ratio's perfect square. Is that right? Area ratio of two triangles, if they're similar to each other, the area ratio will be the similarity ratio's perfect square. And this one can be actually expanded not only to triangle, any shape. It could be a quadrilateral, could be a circle, could be whatever, any shapes. If they are similar to each other, the area ratio would always be the similarity ratio's perfect square. This is extremely important. You're going to see that we're going to use this property from time to time. Okay, in today's sample questions, you're going to see that sometimes a lot of complicated problems just can be solved very easily by using the similarity ratio's perfect square equals to the area ratio. This is very important. Okay. Okay, afterwards, number five, we need to talk about the sine law and the cosine law. Okay, I think the sine law is more straightforward, right? You basically have this. A over sine alpha or sine A, B over sine B, C over sine C equals to 2R. What is this 2R? So what is this R? Who can tell me? What is that? We're very quiet. Yeah, I see Zihan, right? Zihan has correct answer. It's the radius, right? It's the radius of the circumcircle, right? The radius of the circumcircle. So if this is your triangle, you must have a circumcircle, right? This is the radius of the circumcircle. Okay, so this is actually something more straightforward. And the other one is the cosine law. So trust me, cosine law is actually a very, very important tool. From time to time, you'll find out a problem have to use the cosine law to solve the problem. Why? Because cosine law is the very important law that build up the relationship between size and angles. Okay? Cosine law is actually a very powerful law that build up the relationship between size and angles. So that being said, it comes our first conditional reaction, number one. If the question give you some side and ask you to determine the angle, or vice versa, most likely you have to use cosine. Okay? This is our conditional reaction number one in today's lecture. If the question gives you a bunch of side, and then eventually ask you to determine some angle relationship or angle properties, or vice versa, most likely you have to use the cosine law. Okay? So how does cosine law looks like? Cosine law looks like this, right? So let's say cosine A equals to what? B squared C squared minus A squared 2BC, right? So how to remember this? You can try to say kind of you never get what you need or you never get what you want because you want to have the cosine A, but this is gonna minus A, and in the denominator there's only BC. It's kind of like a shortcut for you to remember this. But anyway, so as you can see this cosine law, you see the left-hand side, this is only angle. And the right-hand side, this is only side, right? So this is the very important law that build up the relationship between side and the angle. You see, for the sine law, you have to get some side, get some angle, right? Get some side, get some angle. But the cosine law can put all the angles at one side, all the sides on the other side. So therefore, you will be able to totally segregate size and angle by using the cosine. Okay, remember, this is something very important. All right, moving forward, let's go to section number 6, area of a triangle, or maybe in the future, not only triangles, but some shapes, right? This is actually a very important topic. If you do some statistics for all the Euclid or like the AMC, so on and so forth, you're going to find out most of the time when the question asks you to do some 2D geometry problems, they will focus a lot for the area. Try to determine the area of a triangle, of a polygon, so on and so forth. Of course, if you want to determine the area of a polygon, you might like to cut it into different triangles, right? And do all your calculation in the little triangles and then adding them together. So that being said, having a good understanding for the triangle's area is actually very crucial. So we'll take this opportunity, try to do a little bit summarize how to determine the triangle's area before we move on to different questions. Okay. So there are so many ways to try to determine the area of a given triangle. The first one is actually definition. This is something you learn from elementary school, right? So you got a triangle, uh, like whatever, and you want to decide, okay, this is the height and this is the bottom, right? So 1 over 2 h times a will be the area of your triangle, for sure. And what else? You can do sometimes if you have the two sizes, let's say, I'm going to put it here, A and B, and you have this included angle, right? What you can do is actually 1 over 2 A times B sine theta, right? This is actually using the trigonometry, right? So two sizes and the sinus value of the included angle is going to generate the area as well. So these are something so easy, right? You have to remember from your elementary school. And then what else? The other way is actually using the Heron's formula, right? As long as you know the three sizes of a triangle, ABC, you can directly determine the area of the triangle without calculating the height or the trigonometry, so on and so forth. You can just directly using this, right? You determine S equals to A plus B plus C divided by 2. And then this is going to be what? Under root S minus A, S minus B, S minus C, right? This is something very understandable. And most of the time, this guy could be expanded like a little bit. I don't know if you guys know this. Let's say if I have a cyclic quadrilateral. So if you know cyclic quadrilateral. Cyclic means you can put it into a circle, right? Do you guys know this? I mean, your day school or some other courses, did the teacher told you? If I have a cyclic quadrilateral, I have the four sizes, A, B, C, D. Can I quickly determine the area of this cyclic quadrilateral? Do you guys know this? Without having some complicated calculation, get all these weird things. Can you quickly, just using four sizes, and determine the area of the cyclic quadrilateral? Have you guys noticed? This is very common, very frequently used conclusion. No? Now, don't be shy. If you have any questions, you can put it there. You just do a Pythagorean with the radius. Not necessarily too complicated. Yeah, yeah, of course you can do that. But can you do something more straightforward? Do you know there's like one step method to determine the area? Because sometimes you have to be fast, right? As fast as possible. Okay, no problem. I'll take this opportunity. I'll show you how to do this. You can also let S equals to 2 plus B plus C plus D. And the area will be S minus A, B, C, D. See? This is very similar to the Heron's formula. Is that correct? Very similar to the Heron's formula. Because why does this work for all the quadrilateral? No, it only works for the cyclic quadrilateral. Yeah, Jason got a question. Does it work for all the quadrilaterals? Unfortunately, no. It's only the cyclic quadrilateral. Like a little bit background you can see from that. You see why you have such a thing. In our regular lectures, we give you guys more inside explanations, but our bootcamp is just going to focus something high level. As long as you have a shape could be cyclic, you can have something similar. Let's say for triangle, of course, all the triangles, they're cyclic, right? Any triangle, you can find a circle, a circumcircle. So triangle have such a formula. But for quadrilateral, not all the quadrilaterals are cyclic. Only a small portion of the quadrilaterals are cyclic, right? So therefore, for the cyclic ones, you can actually have a very similar formula. Okay, same thing. If you have a polygon, they're like a cyclic. You can also have something similar. But if you have like just like a random quadrilateral or random polygon, there's no way for you to do this. Okay, this is something I want you guys to remember. So far, so good. All right. And I think this is basically like the high level thing we like to say, right? Yeah? Basically, how to use this, try to determine the area of this triangle, different ways. These are something so easy. And there's another thing I want to mention is the shoelace theorem. This is more like a coordinate geometry thing, but I really like to put it here because this is also a very important technology. Let's say in the Cartesian plane, right? And oops. Okay. Let's say in this Cartesian plane, you have like three points, A, B, C. Is A, B, C, right? You create a triangle ABC. How can you determine the area of this triangle? How to do how can you determine the area of a triangle if I give you the coordinate of the three sizes? Well, one way is that you try to use like the distance, right? How to determine the distance between 2 points. You find this is maybe C. You find here this is maybe B. You find here this is maybe A, and then using the Heron's formula. But this is going to be a disaster. Right? You have to do 3 times calculation and then taking from there. So there's a very straightforward way to try to do that is using the shoelace. This is what we call the shoelace theorem. You can determine the area of a triangle by using the coordinates of the three sides of the three like vertex. Right? I think you guys all know this, right? Can I have some feedbacks? This is a very common, understandable thing, right? Yeah. Okay. Yeah, you just type it into the group chat. I'm actually monitoring the group chat all the time. Don't be shy, right? So if you have any like opinions, I mean, you have some different questions or something, just let us know. Yes. And this is like the famous shoelace. And shoelace is actually not only for triangles. You can expand it into any convex polygons. Convex polygons. So first, I have to ask you, do you guys know what is a convex polygon? Or what is the other side, or say the convex polygon? Do you guys notice? Okay. A student said like Federer, Federer? Not like Federer. So I don't know how to say your name. Federer? Federal. But anyway, yes. So what is that? Convex. Okay, convex means for this polygon, for instance, I'll give an example. For this polygon, you take any side. I'm not saying only one side, right? Any side. Let's say I take this side. I make an extension for the side, make a line. The entire polygon must be on the same side of this line. You see, this entire polygon is here, right? It's actually on the lower end of this green line. Something similar, you can do any line from here or from here. Regardless where you pick up your line, right? You can always make sure your entire shape is on the one side of your extension. So this is going to be a convex. But if I have something like this is not exactly the same. Let's say if I choose this line, this is one of my side, right? I do an extension. I can find part of my polygon is lower side, part of my polygon is like on the upper side. So that being said, this is not a convex, it's a convex polygon. In our high school territory, all our discussion focus on the convex polygon. We do not like to discuss any properties for the convex polygon. Okay, this is something I like to make a little bit explanation. Okay, so what is the more generic thing? So now I know this is the like the shoelace law for the triangle, which has three sizes. If I make it into more generic, I have a polygon, convex polygon, which has n sizes, which has n points. So like n vertices, I can do exactly the same thing. You just basically have to remember this. This is going to help you to remember how to determine the area of a given convex polygon in the 2D Cartesian plane. Okay, we can talk about more whenever we go to the coordinate geometry section, but since this is talking about the area, I like to put it here. Just give you guys a little bit summary. Okay. The other one is the famous Stewart. You have to remember. Stewart means that. Let's say I have any triangle. So let's say triangle ABC. I find a dynamic point D on the BC side. As you can see, you have like what? 1, 2, 3, 4, 5. We'll say this is A, okay? A, right? The opposite side of A angle is A. 6, right? You have like 6 segments. 6 segments, right? So actually, there is a intrinsic relationship between these 6 segments. Okay? Like I said, this is a given any shape for any given triangles. I do not really ask to be obtuse or acute. No. There's anything, any kind of triangles. As long as I find a dynamic point on one of the sides, I do one connection, so I will form up 6 different segments, and there's a relationship for the 6. M times A times N plus D plus A times D equals to B times M times B plus C times N times C. So that being said means what? As long as you know 5 segments, you will be able to find the 6th one. There's a relationship between the 6 segments. They're not like totally independent. As long as 5 has been set, the 6th one, the last one, could be calculated directly. Okay, so first, I don't know if you guys know this. Have you guys heard about this Stewart method or like Stewart theorem? Can I have some feedbacks? This is very important. Trust me. Sometimes if you use the Stewart, it's really going to help you to expedite your calculation. There's no, what should I say? There's like, this really going to help you to calculate really fast. You don't have to do a complicated cosine law thing, blah, blah, blah. Just make it very fast. Yeah. And do you guys know how to prove it? We're not going to take it here because this is a bootcamp lectures. We're not going to explain too much. We just summarize the most important thing, and you guys go back to do some Google research. Do you know how to prove it? What is the technology you're going to use to prove it? Have you ever learned this? Yeah, I see Penny has the correct answer. That's the cosine law. You will use the cosine law to basically prove this, like the Stillwater theorem. You can do some Google research these days, right? Like so easy. Do some Google research, ask ChatGPT. They're going to give you the correct answer, proving process. All right. So this is for the seventh one, the Stillwater theorem. And number 8 and number 9, they're also very important, especially from AMC AIME's perspective. Maybe for Euclid, they do not really test you too much so far, but it's always good to tell you these two very important rules. These are the two kind of also like a twin brother. They always come in pairs. So the first one is the famous Menelaus. Menelaus means what? Let's say I have a triangle. This is my triangle, ABC. I have a transversal line. It's actually any random transversal line, okay, which cut my AB side, intersect at BC side, and also the extension of AC side, okay? As long as you have this, you will have such a relationship. It's kind of like starting from anyone. Let's say I'm starting from here, AR over RB, BP over PC, CQ over QA. You just basically do a circle around this entire triangle. So the one, two, three different proportions, multiply them together equals to 1. This is a very important one. I think AMC tested not from time to time, but occasionally from time to time. Yeah, occasionally. Not every time, but very occasionally. And AIME actually use it a lot. Okay. So the other one is also the very famous Siva theorem. Siva theorem said that, let's say you have a triangle, any kind of random triangle ABC. You have a random point, X here, okay? And you do a little bit connection, extension, so on and so forth. And then you'll be able to find out what? AF over FB times BD over DA times EC over EA. Basically, also you take a circle. Take a circle. AF, FB, BD, DC, CE, EA. Okay, take a circle. And then you basically multiply those three things together, three proportions together, is also equals to 1. You see, there's a lot of similarities between the Menelaus and the Siva theorem. Okay, so far so good. I think these are the most important theorems that you need to know in order to go to Euclid. If you want to go to AIME, you have to know a little bit more than that, but it's okay. For Euclid, it's okay. It's good enough. Our lecture just focus on Euclid for now. So these are the most important things that you need to remember before you go to Euclid. So far, so good? Okay. So this actually wraps up our section number 1. Now, let's go to our step number 2. Before we jump to the real problems, step number 2 is let's try to do some summary. What are the classical problems in Euclid? Talking about the 2D geometry part, the triangle, quadrilateral. What are the major problems you're looking at? The first category is similarities. Triangle, especially focus on the triangle. Triangle's similarity. You basically need to remember first is the property of the similarity, right? Two triangles are similar to each other. The sides are proportional and the areas, I mean, like the angles are the same. This is actually very important. And one of the most important thing is you need to remember the area ratio is the similarity ratios for fixed square. The second one is actually even more important than the first one because from time to time, you see a lot of problems focus on testing the area ratio, similarity ratio related stuff. So this is the first part that AMC love to test you from time to time. The second part is sometimes when you're dealing with a relatively difficult geometry problem, try to use trigonometry to solve geometry problem. This is actually a very important thing. Try to use some trigonometry to solve the geometry problem. You're going to find out, especially in some like sample questions I'm going to be giving you today, you'll find out if you just go for the typical geometry way, it takes too long. Later, I'm going to show you the comparison, my solution and the official solution from Euclid. The official solution from Euclid is very, very long. Like I keep saying, not to say you just figure out that solution within 2.5 hours. You just copy that solution, write them down. It's going to take more than 2.5 hours. So therefore, you need to find some faster way to solve the problem. I find out actually, if you always can open your door to some trigonometry way, it's really going to help you to expedite your calculation significantly. Okay, that's the second part I want to say. So the trigonometry and also cosine law. Like I said, right? Cosine law is the best law which give you the relationship between the sides and the angles, right? So try to bear in mind there are some cosine law. Try to bear in mind there are some trigonometry tricks you can do. Really going to help you a lot for some complicated geometry problems. We're going to talk about it in a bit. And the third one is actually the area. Try to determine the area of different triangles or different shapes. Like I said, are very important. We just introduced some rules, some formulas, right? How to do the area calculation. But I still want to give you one step forward. Generally speaking, in the Euclid Math, okay, if you want to determine some complex areas, there are actually four major ways. Four major problems. The first one is using definition. This is easy. Using definition, right? Use like whatever definition or whatever formula, right? You can basically plug in the formula and do the calculation. That's it. The second one is rotation strategy. So what is a rotation? Sometimes you see a shape is here, but you can't solve the problem whenever the shape is there. You have to rotate the shape to here. Rotate the shape to here to solve the problem. Because as long as you do a rotation, the first shape and the second shape, they are actually congruent to each other. Is that right? If you rotate a shape, you do not change it. You just basically rotate, right? You can rotate maybe versus a point or something like whatever, right? So as long as you do the rotation, you'll actually make another congruent copy of your original shape. You kind of like what? Transfer your shape from one place to the other, right? Rotation. We're going to give you sample problems. You will understand where I come from. So this is one way to try to solve some geometry problems in Euclid. The third way is compensation. Compensation means what? Let's say I have a shape like this. I want you to determine the area of this little weird triangle, like little weird quadrilateral thing. Maybe for some reason there's no way for you to do it, but you can kind of like do a little bit compensation to make it into a big triangle. And then for some reason, maybe you figure out the area of this little green ones, and then you'll be able to find out, right? The total area minus those two green areas is going to be your quadrilateral. So this is more like what we said, a compensation to make it from a weird or some strange shape into something you are familiar with. Familiar with. Okay? The question might give you a very rare, very strange shape. You want a little bit compensation to add something here, add something there, make sure you get what you need. Okay, later I'm going to give you the problems. We can take it from there. And then number 4, partition. Partition and compensation, they're kind of like opposite, right? Compensation is make them together, make it big, but partition is actually cut. I have a shape like this, but maybe I have to cut it into 2 little triangles and then do the calculation one after another. So these are the 4 major ways how we deal with problems in the Euclid Math. We're going to give you problems, sample problems, one after another. And then I'll give you I'll give you more like high level summaries, then you will know what to do. Okay, so far so good. Any questions? Are we all good? It is very important that you follow me, and I'll be asking you a lot of questions from time to time. Very important. All right, so this is our step number 2. We try to do a little bit like high level summary. We're going to do the same thing for every single lecture, summarize all those important problems for each of this category. But generally speaking, this is our 1, 2, 3, 3 steps. Now let's go to our step number 3. Let's go for some real problems. Real problems. Okay. So, like I said, I break it into 1, 2, 3, 1, 2, 3 major categories. Let's get started to each of them one by one. Let's go to the first one. Similarity. Similarity related problems. Okay, let's go to our first problem. Okay, our first problem is a problem that comes from here. This is a problem that comes from 2007 Euclid, question number 8, B part. Okay, we tend to give you some relatively difficult problem, right? Not something super, super easy. Okay, let's have a quick look at it about this problem. The problem says in the diagram, the area of triangle ABC, the big area is actually 1. Trapezoid DEFG. DEFG, this guy. Okay, this guy is constructed so that G is on the left of F, DE is parallel. Okay, you need to highlight all those important concepts, right? Parallel to BC, EF is parallel to AB, and DG is parallel to AC. Basically, all the 4 sizes, they're actually parallel to one another. Okay? With all those information, the question asks you to determine what is the maximum possible area of this trapezoid DFG. Okay. I got a big triangle and I got a little trapezoid, like the red trapezoid in the middle. And the question asks you to determine what is the maximum area of this little trapezoid. So how do we think? I like to teach you the thinking process. Well, try to determine the trapezoid. Of course, I know how to determine the trapezoid, right? The top, the bottom, the height, stuff like that. But I really have no idea what is the E, what is the GF, then not to say what is the height, right? So to directly calculate the area of the trapezoid might not be very handy because you have nothing, no idea. So that being said, maybe let's try to do a little bit of observation. In order to determine the area of this trapezoid, we can have a quick look at it about these guys. We have a triangle here, right? This is the green triangle. We have a blue triangle here. And we have a yellow triangle here. Those 3 triangles if I give a number 1, 2, 3, you can find out, is there any specialties for those three triangles? Triangle 1, triangle 2, triangle 3. Who can tell me? Can you put it into the group chat or you can just talk? Is there anything special for those three triangles or just like random triangles?
Are they all similar?
Exactly, right? They're all similar to each other and also they're similar to the big triangle ABC, right? So triangle number 1, similar to the number 2, similar to number 3, and similar to triangle ABC. If you can remember what we talked previously, as long as you have the similarity and the question asks you some area, you can do what? You can try to understand the similarities ratio's perfect square is going to be the area ratio. Is that correct? So area is going to be the similarities ratio's perfect square. So that being said, those 1, 2, 3 triangles, they all have some relationship for the triangle ABC. If that's the case, maybe in order to determine my trapezoid, the best way is just to use triangle ABC's area minus number 1, number 2, number 3, right? I need to use the relationship between those little triangles. And moving from there, we're going to be able to solve the problem. Okay, so let's have a quick look at it. Triangle ABC's area is 1. So my goal is try to determine how to do this. Number 1, number 2, number 3's area. Okay, like I said, they are similar to each other, then I must have to use the similarity to make it work. Okay, so how to make up the similarity? Let's try to do one thing. We know BG over BC is the same as BD over AB, right? BG, BC, BD, AB. We can say this is maybe K. Okay? Of course, K is between 0 and 1, which makes sense, right? Let's have a quick look at it. Using this information, can I quickly determine the area of all those little triangles? Let's have a quick look. So that being said, okay, let's say I'm going to erase this part. Let's say this is my triangle. This is A. The total length is A. This is B. This is C. Because you're telling me that BG over GC is actually K. So that being said, this part is going to be KA, right? So this part is going to be KC. So this part is going to be what? 1 minus KC. Does it make sense? Okay, because DE is parallel to BC. If this part is 1 minus KC, this part is going to be what? 1 minus KB. Does it make sense? 1 minus KB. This is quite understandable, right? Because parallel line, you can actually transfer this proportional relationship. So if this part is 1 minus KB, this is going to be KB, right? EC is going to be KB. Again, because you have what? EF. Change the color to black. EF is parallel to AB. So if this part is KB, so this part is going to be what? KC, right? Okay, excuse me. Yeah, because this part is A. Does it make sense? I think this is a very understandable process, right? You just basically transfer. Okay, student question. Jason has question. Why it is 1 minus 1K? Yeah, because the total one is A. Yeah. This is C, right? KC. You don't understand? Okay, no problem. Yeah, because the total AD plus DB is actually equals to C, right? DB equals to KC. So therefore, AD equals to 1 minus KC. Does it make sense? Jason, it answers your question? This part is KC, so this part is 1 minus KC because adding them together is actually C. Okay, yeah, any question, just let me know. So yeah, so this is an open course, but as long as we go to our real courses, we have lesser students, there will be more target. You can actually just talk. Okay, so that's the case. I think we can just gradually give the area for S1, S2, S3. Let's do this one by one. For triangle number one, you're telling me you are similar to triangle ABC, right? So, and what is the similarity ratio? Triangle number one is here. The similarity ratio will be 1 minus K. Is that right? So if the ABC area is 1, this is given by the problem. ABC area is equal to 1. So this is 1 minus K perfect square. Okay? So what about the number 2? Triangle number 2 is also similar to triangle ABC. And what is the ratio? Number 2 is here. The ratio is going to be K. Is that right? So if this area is 1, this area is going to be K squared. Same thing, number 3 is similar to ABC. And the ratio is what? Number 3 is here. The ratio is actually K, right? Also K. So the ratio is K. If this is 1, this is K squared. So what you have to do is you basically subtract to here, insert to here, replace to here. Does it make sense? This is quite understandable, right? You have already determined the area of your triangle number 1, number 2, number 3. Just insert it into this original expression, and then you will be able to determine the total area of the triangle of the entire trapezoid. Okay, Penny got a question. Does it mean that triangle 2 and 3, they're congruent? Triangle 2, yes. Triangle 2, 3, they are kind of, they're not congruent. They're similar to each other. They're similar to each other. They're not congruent. Why? I can answer your question very quickly. That's a good question. Let's say here. The side is KC, KA, KB, KA. You see, one is actually, so let me see, are they congruent to each other? KC, KA? No, they're just like similar to each other. There's no guarantee to be congruent. Yeah. But they're very alike, right? The similarity ratio is actually very correct. Okay, so let's continue. Now you can actually insert it into the original expression, and then let's try to see how this trapezoid looks like. So this trapezoid as trapezoid, we just basically plug in the value 1 minus K squared minus K squared, 1 minus K minus 1K squared. So it actually equals to 2K minus 3K squared. Okay, that's the trapezoid area. That's the trapezoid area. Okay, so far so good? Okay, so let me get back to here. They are congruent or not? I think they should be congruent. Because you know what? Definitely these two triangles, they are, okay, they are similar to each other, right? They're similar to each other. And on top of that, they have already got a side which are the same. This is KC, this is KC, right? If you have two sides, this KC, KB, K, yeah, this would be KB. Yeah, I think it should be, I think they should be congruent to each other because two similar triangles, as long as you have two sizes, they are equal to each other. So these two similar triangles will convert into congruent triangles. Does it make sense? Two similar triangles, if they have two sizes, they're actually equal to each other, then automatically it becomes congruent to each other. Yeah, I think this is a good catch. And also they have the same area, you see? The areas are the same. They're similar to each other, the areas are the same, the two sizes are the same. Definitely they're congruent to each other. Right? Make sense? All right, so let's continue. Now we're actually having the expression of the trapezoid, and we know K is actually from 0 and 1. The question asks you to determine what is the max of this value. What is the max of this value? Can you do it very quickly? This is something so easy, right? You can do this very quickly. So you can basically using what? Using the just like the using like the polynomial or using the quadratic function, you'll be able to find out the maximum value, right? So this is like what? What is the shape of this graph? This is a quadratic facing down, right? And it actually goes to this is your like the symmetric axis, right? So this is from 0 to 1. The maximum value is actually here, right? So S trapezoid, maximum value is whenever 2k minus 3k squared, whenever k equals to 1 over 3. And you'll be able to get your maximum value. Does it make sense? Right? So you see, this is actually a very straightforward way how to solve this problem using the similarity areas, similarity, and the area ratio. And one more thing is that, you know what? Actually, whenever you write this solution, you can just write it this way. There's no need for you to write an essay, give all the super details. You can just basically use this way. When I mark the Euclid exam, I mark the Euclid exam from time to time. So I don't really ask you to give me a essay, have all the super details. As long as you list out the most important things, maybe using a little bit of English, but not too many, I will be able to understand what you need. So try to save your time. Do not write too much too long. And this is good enough for you to get the full marks. I'm not reading this is not an English exam, right? I just want to have your correct answer. That's it. Okay, this is our question number 1. If all good, let's go to our question number 2. Our question number 2 is a problem. Okay, this is a problem that comes from 2011. Oh, I mean 2001. Euclid, question number 9. Okay, let's have a quick look at it about this problem. So this problem says triangle ABC is right angled at B and has side lengths. I use the color red. Side lengths which are integers. Side lengths which are integers. This is actually a very important conditional reaction number 2 in today's lecture. As long as you're dealing with something, let's say a side, the side length does not have to be integer, right? It could be any numbers. Okay, for something could be any numbers, but the question really asks you, this has to be an integer. Most likely, this problem is going to have some basic number theory related discussion. Most likely, maybe doing some at least factorizations. This is very important. You know, if I ask you like your age should be always an integer, right? But like an angle, like the measurement of an angle, a length of a side, this does not have to be integer. For something does not have to be integer, but the question give you an integer, most likely you have to have kind of like a little bell ring saying that there might be something there. You have to think about it. Most likely, this could be some interaction with the number theory, with some factorizations moving forward. So let's continue. A second right triangle PQR is located inside the ABC as shown, such that its sides are parallel to the sides of ABC. You see, quite likely to our previous question, you have a triangle and you have a shape inside that are parallel to the three sizes of the triangle. You see, our problem is a trapezoid, but it's also parallel to the three sizes. So this guy is a triangle inside a triangle and parallel to the three sizes. And the distance to the three sizes between the two parallel lines are always 2. This is 2, 2, 2. Okay? So determine the side lengths of all possible triangles ABC such that the area of triangle ABC is 9 times of the triangle PQR. 9 times of the triangle PQR. So this guy, I'm going to write it. Triangle ABC's area is 9 times of triangle PQC. PQC and ABC, obviously, they're similar to each other, right? So, like I keep saying, this is the conditional react. We keep saying, as long as you see two triangles, they're similar to each other, if the question gives you the area relationship, automatically you know that the similarity ratio between the triangle ABC and the little triangle PQR is going to be 3 to 1. Does it make sense? This is a very understandable process. The similarity between the three things is going to be between the little triangle and big one should be 3 to 1. Okay. The question is asking for what? The question is asking determine all the side lengths of possible ABC to make sure, the little one and the big one has the area 9 to 1, aka the similarity ratio 3 to 1. So our goal is to determine the side of ABC. Okay, if you want to determine ABC, maybe this is C, this is A, this is B. Okay, we already know what? We already know the similarity ratio between those two triangles is 3 to 1. So that being said, this is going to be what? C minus 3, C over 3, A over 3, B over 3, right? This is quite understandable. Okay, now I need to determine the ABC's length. And I know the similarity ratio. I know the area is 9 times. Most likely, I need to build up some relationship between the ABC, right? I need to have an equation. I need to have some relationship before I can determine ABC. So the next $1,000,000 question is, how can I build up the relationship between the little one in the middle and the big one outside? Who can tell me? How can I build up the relationship between the little red one and the big white one? It looks like the only condition the question gave you is the area is 9 times apart. That's it. You have no more information. Who can tell me? How can I build up the relationship? Like I said, I see there's a area related discussion, right? The only thing I have is area. Most likely I have to do all my analysis based on the area, right? That's the only thing that I can do. But how can I build up the relationship between these two areas? I think the most straightforward way is I need to represent the big triangle ABC's area, maybe using the small area and some white regions, right? I need to represent triangle ABC's area, maybe using triangle PQR's area. But how can I do that? I think intuitively, I need to do a little bit auxiliary line. I need to break it like this. So if I want to represent this ABC's area, what I can do is I can try to break it into different regions. The green one, the black one, and the yellow one. You see, the black one, the green one, the yellow one, they're all what? Trapezoid. Is that correct? So it looks like three trapezoid plus the little red triangle in the middle, they build up the entire triangle ABC's area. Make sense? Okay, so at least I have an equation here, right? I say my triangle ABC's area equals to my triangle PQR's area plus trapezoid APQB, APRC, trapezoid, and BQRC. Right? Let's have a quick look at it. My PQR, we have already know that, right? This is 1/3. This is like 1/9 of my entire ABC, right? So my triangle ABC is 1/2 A times C. And my little one in the middle is actually 1/2 A times C divided by 9. Okay? Then what about my APQB, my black one? My black one, this is like a trapezoid, right? I have the top, I have the bottom, and I have the height. It's 2. So 1/2 C plus 1/3 C times 2, right? And then my green one, APRC, is 1/2 top, bottom, 2. And the last one, 1/2 top, bottom, 2. Does it make sense? This is a very easy peasy understandable process, right? That's the only thing that you know in this problem. The problem does not give you any angle, any other stuff. There's only some area. Okay? Now let's try to simplify this. It's going to go to AC equals to 3C, 3B, 3A. Okay. Now I have one equation, but I have 3 variables. There's no way for me to solve the problem. If I want to reduce the variable a little bit, how can I do? I have 3 variables. I have only one equation, right? There's no way for me to move forward. I have to at least reduce one, right? Yeah, I see Penny has the correct answer and Matthew as well. Of course, you have, this is like a right triangle, right? Right triangle, you have the Pythagorean theorem. That's the only thing that can help you reduce the complexity like a little bit. So B square equals to A square plus C square, right? So which one to represent? I think let's try to replace B. Why? Because there's AC here. If I want to replace A or replace C, there will be an under root, blah, 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 and then times C. It's very weird, right? Let's try to make my life a little bit easier because B is standing here as a standalone parameter, but AC already multiple them together. Let's try to replace B. B equals to, I'm going to put it here. And then you're going to do some simplification, do a perfect square on the 2 sizes, so on and so forth. All the way you get here. AC minus 6C minus 6A plus 18 equals to 0. Do some quick calculation. We're going to ignore the calculation in our lectures. You get this? Whenever you get this, who can tell me? What is your conditional react taking from here? Don't forget, A, C, they're both integers. What is your conditional react as long as you see such an expression? Yes, I see Penny has the correct answer. We're going to do what? Simon's favorite factorization trick. Is it right? This is a very important conditional react number 3 we talk about here. As long as you see such a shape, your first reaction is try to do the Simon's favorite factorization trick. We have already talked about it in our regular lectures. So here, I'm not going to unfold it too much. If you have no idea what it is, I can provide you some information. You can talk to me offline. I'll provide you some links. This is extremely important. So this is going to go to A minus 6, C minus 6 equals to 18. Okay? Okay. So all the way comes to here. This is actually a very standard formal process. You don't really have to think too much. So what you have to do is we just basically follow them one by one. Whenever you have this, the next step is going to be doing what? So because A minus 6, C minus 6, they're actually integers, right? Because A and C, they're both integers. The minus 6, they're integers. So they will be the factor of 18, right? They're both factors of 18. Okay, if they're both factors of 18, then that being said, you just have to list out all the factors of 18. A minus C, C minus C, they could be what? 18, 1, 9, 2, 6, 3, minus 3, minus 6, minus 2, minus 9, minus 1, minus 18. You can keep writing, right? It could be also the next one is what? This could be minus 18, minus 1, or minus 9, minus 2, right? All those kind of like you're taking reversely, right? Because you don't know which is 1, which is minus 1. I mean, because you don't know which is minus 1, which is minus 18. Could be A minus 6, could be C minus 6, right? You, you guys follow me? This is important, right? Because normally speaking, you need to basically find out, right, the alternative, list out all those scenarios. But most of the time, you do not have to because we're going to give you a conditional react number 4. As long as you're doing some discussion, you know, A minus 6, C minus 6. The question is not really asking you who is A, who is C, right? The question is asking you how many scenarios, what are the possible triangle ABCs? Who is A, who is C, it doesn't matter. As long as got a pair ABC, this is good enough, right? So that being said, A and C, they are actually identical in this problem. You don't really care who is A, who is C. They're pretty much identical. So that being said, as long as you find some identical stuffs, instead of doing all those kind of scenarios, permutation one of another, you can do a very important assumption. We always, without the loss of generality, we can let A greater than C. This is very important. It's really going to help you to save your discussion, save your casework. As long as two numbers or two variables, they're identical, or who is not so important during our calculation process, we ask you guys to maybe let one is greater than the other without a loss of generality. That's really going to help you to reduce your calculation significantly. There's no need for you to figure out all those different scenarios. You just figure out one side and the other side will be exactly the same. You guys follow me? This, this is good? Okay. Yeah, you can give me some feedbacks in the group chat. So this is important because this is really going to help you to significantly reduce your calculation. So that being said, I just need to care about this part. Because A is greater than C, A minus 6 is greater than C minus 6. I have to make the bigger one for the A minus 6, the lower one for C minus 6. So all this are irrelevant. I can ignore it. Okay, so moving forward, I think this is fairly easy. You just have to do some calculation, right? A minus 6, C minus 6, right? There's so many different scenarios. Just do the calculation one by one. You'll find out you have only A can be 24, 15, 12. C can be 7, 8, 9. These are the three pairs possible solutions. Of course, B, you can use the Pythagorean, 25, 17, and 15. So that being said, you have three pairs of potential solutions. So far, so good. A very quick recap for this problem. I think this problem actually has some important conditional react. So first conditional react is that as long as the question give you, I'm going to highlight it using color black. As long as the question give you some integers, some integers for the variable that does not have to be integers, bear in mind, you might have to use some factorization. Second, similar triangle, you see the area relationship. Absolutely, you want to use the similarities ratio's perfect square equals to the area ratio. Okay, moving forward, as long as you see something like this is a conditional react number 3, try to use the Simon's favorite factorization trick. Important, you have to remember this. And then during the calculation process, as long as you find two variables that are identical to each other, then without a loss of generality, you need to remove like which one is bigger. Which one is bigger, which one is smaller. Just try to say, okay, without a loss of generality, one is bigger than the other. That you can significantly reduce your calculation process. So far, so good. So this is our second problem. I think two problems is good enough. It really gives you an idea that in order to calculate, in order to do the area, whenever you see the two triangles that are similar to each other, bear in mind, similarities ratios perfect square really going to help you to save your time. Okay, this is our first category, talking about the similarities property, so on and so forth. A student got a question, but then after you solve A is greater than C, do you need to double the number solution if C is greater than no? Because the question does not really care. You see, the question is determine all possible triangles ABC, blah, blah, blah. ABC, who is A? Like in the ABC, you have three sizes, right? But who is A, who is B, who is C? This is solely determined by you. There's no need for you to have like two pairs. Let's say you have a solution, 3, 4, 5. This is one solution, good enough. Because you're telling me this is like your A, this is your C, this is your B, or this is C, this is A, this is B. I don't really care. This is, to me, this is only one triangle. Okay? So that's the reason why we like to simplify our calculation just without a loss of generality. A is greater than B, which is B greater than C, that can make your calculation process more straightforward. Perfect. Yeah, any question, just let me know. We can answer. This is our live lecture, right? We can basically answer all the questions on the fly. Now let's go to the second category. Try to use some trigonometry to solve some geometry problem. Let's have a quick look at it. So question number 2, there you go. This is the first problem. The first problem, we're looking at a problem that comes from 2018. Euclid, question number 8, B part. Okay, let's have a quick look at it. So this problem says, in the diagram, rectangle PQRS is placed inside the rectangle ABCD in two different ways. First, with Q at B, R at C. So basically the triangle, the rectangle is actually put it in the corner, right? So the Q is superpositioning with B, the R is also superposition with C, which makes sense, right? And then the second time is actually you tilt it. Secondly, with P is here. S, RQ. You actually tilt it in the middle. Make sure P, Q, S, R are actually on the two sides of this square. All right. And then if AB equals to 718. AB equals to 718. And PQ equals to 250. So this is also 250, right? Okay. Then determine the length of BC. What is the length of BC? How to do such a problem? So first, if you check the official solution from Euclid in this problem, it's crazy. It's very lengthy, a lot of calculation. Later I'm going to show you. But now I'm going to say, as long as you use some trigonometry, you can significantly reduce the complexity of such a problem. Let's have a look at it. Let me try to show you how to use the similarity, how to use the trigonometry, try to solve the problem. So if you want to talk about the trigonometry, you need to have some angles, right? Trigonometry comes from angles. So to make our life easier, I'm going to say this is my angle theta. Okay, if this guy is theta, this guy is a theta as well. Any objections? You guys follow me? If I see angle BPQ is theta, then automatically my angle CQR is also theta. You guys follow me? Do I have to explain why, where does it come from? Why? Yes, no? Can I have some feedbacks? Are we all good? Yeah, I see Penny has. Yeah, so if you want to, yeah, if you have any questions, you need to talk to me. Try to communicate with the teachers, right? This is like an online course. But even though this is like face-to-face, in-person course, if you don't follow the teacher, right? So that I can't read your mind. So yeah, you can just follow me, right? Yeah, assume like Penny follow me. Okay, the other student. So if you're silent, I assume you say a yes. If this is Q, this is also Q as well, right? I mean, if this is theta, this is also theta as well. This is something quite understandable, right? Okay. In that case, I think we can actually solve this problem just to use this thetas. Something very quick. Let's have a very quick look at it. So let's say I have a DC, or here. DC is actually what? dr plus rc, is it right? dr and rc. What is dr? If this is 250, dr equals to 250 times cosine theta. Is it right? This is understandable, right? dr, I'll change a different color. dr equals 250 times cosine theta. And RC, you're telling me what? RC is here. RC, this is BC, right? Because QR and BC, they're superpositioned together, right? So this is BC, this is BC. So therefore, RC equals to BC times the sine theta. And this value equals to 718, right? This 718, this is 718, 718. This is very understandable, right? No, there's no rocket science, quite understandable. Okay, now you finish your calculation for BR, for DC. Let's try to do BC. BC equals to BQ plus QC. What is BQ? BQ is 250 times sine theta, right? They're very symmetric. And what about QC? QC is BC times cosine theta. This guy equals to BC. You guys follow me? This is something quite understandable, right? Nothing too complicated. You just try to solve them, right? That's it. Now I have two equations. First equation, second equation. Okay, I'm going to do a very little, very easy, brief trigonometry calculation. From the second part, I want to find out, let me try to find out the value for BC. BC equals to 250 sine theta, 1 minus cosine theta. This is number 3, right? Now I need to insert number 3 into equation number 1. Insert it into equation number 1. Try to replace BC, right? Then you have what? 250 cosine theta, 250 sine theta, 1 minus cosine theta, sine theta equals to 718. Is that correct? You guys follow me? This is a very easy calculation, right? Nothing too complicated. Yes or no? Can I have some feedbacks? Are we all good? All good, right? Perfect. Now, I think this is a very typical trigonometry thing. These together is actually equals to sine square theta. Sine square theta, this is 1 minus cosine theta. What can you do? Who can tell me? Is there any way for me to do some further simplification? Yeah, I see Sean has the correct answer. Yes, this guy equals to 1 minus cosine square theta equals to 1 minus cosine 1 plus cosine. Is that right? This is so easy. And you can cancel out those two, 1 minus cosine. This is very easy, very understandable trigonometry stuff, right? Nothing too complicated. Okay, if that's the case, you can further simplify. This is going to be 250 cosine theta, 250 1 plus cosine theta equals to 718. You solve this equation, cosine theta equals to 117, 125. Sorry about the numbers, like the number a little bit shitty, but it's okay. Cosine theta. And then as long as you get a value for cosine theta, you can easily find a value for sine theta, right? You see, these are all acute angles, nothing too complicated. So it's going to be 1 minus cosine square theta. Okay, now you have your value for cosine theta. You have your value for sine theta. You just put a value to here. You can easily get a value of BC, right? So therefore, BC equals to 1375 QED. You see? Very easy, very brief. You just need a couple of lines. No more than 8 lines, right? You finish the problem. Because I have to give you a little bit of explanations and write a bit more, but you can consolidate it only lesser than 10 lines. You've finished all the problems. You see? Using the trigonometry really helps you to do the calculation very quick. Okay, how does the Euclid official solution looks like? I'm going to show you the Euclid official solution. We're not going to go to the super details of it, but you'll be able to see. Very lengthy. It uses a lot of similarity. So I'm going to drop it to here. One sec. Like two. Oops. Yeah, I need to put it here. So what I'm trying to say, it actually uses a lot of similarity and then try to use the area and they'll use the Pythagorean similarity and do a lot of complicated calculations. It's very complicated. Calculating the area here and there and similarity, a lot of like similar triangles. You know what? That's not very high efficient. Using our strategy, you just use the easy peasy way like this, and then you'll be able to solve the solution fairly quick. So far, so good. This is the beauty of using the trigonometry, try to solve the problem. Okay? Actually, because you know what? This problem is very alike to AMC 2014, AMC 12B, question number 21. I like to give you the problem. You have a look at it. They're pretty much the same problem. See? Look, they're exactly the same problem. Euclid actually break the same problem, the same graph into two, but AMC is basically put them together into the same shape. But what I'm trying to say is that there's a lot of similarities between the Euclid and AMC. So Euclid, you see, we do not have so many papers, so many exam papers, only 10 problems per year. But AMC have A, have B, there are so many years. So whenever you try to do some preparations for the Euclid, feel free to use the AMC. There are a lot of problems are very similar. They copy from one just back and forth. Okay? So you see, this is actually using the trigonometry. You can solve the problem very quick. I'm going to give you another problem, another sample problem, and you'll be able to see the same thing. So the second problem is actually a problem that comes from here. Okay. This problem is a problem. This is a question number 10. Trust me, this is an easy problem as long as it uses trigonometry. 2001, Euclid, question number 10. So this problem, let's have a quick look at it. Mhm. So for this problem, it's a problem says point P and Q, they're located inside a square ABCD such that DB is parallel to QB. Okay, I'm going to highlight it. This guy is parallel to this guy. Okay? And DB, DP, QP, QB, they're all the same. The three red segments, they're the same. Okay? With all those information, the question asks you to determine the minimum possible value of angle ADP. The minimum possible value of angle ADP. Okay. As long as you see a minimum possible value, this is our conditional react number 5. As long as the question asks you to say some minimum, maximum, or something, of course you know you have to have some inequalities, right? If the question asks you to do some minimum, maximum, and so on and so forth, the most straightforward way for you to do is actually using the inequality. Inequality can help you do this kind of thing, right? This is conditional react number 5. And one more thing is that the question give you some side relationship, right? It says the three sides are the same. Right? PD, QD, QB, the three sizes are the same. And then the question asks for an angle relationship. Do you still remember, in order to make this happen, what kind of rules I need to use? This is our conditional react number 6. Still remember what kind of rules can help you to do the side relationship and angle relationship integration? Yes, the cosine law, right? So these are actually very important conditional react. You need to do some cosine law to make sure you can find out this relationship. Okay, let's try to do this problem using the cosine law. We have a big direction, right? We need to build up a relationship. So this is more like an inequality. And in this inequality, we kind of to use the cosine law try to solve the problem. Taking from there, maybe we can solve the problem. Okay. But this problem, one of the most challenging part of this problem is there's actually a PQ segment. The PQ segment is actually flying there, right? Flying there in the middle of the square. So I have to put it into a triangle in order to make it work, right? If it's flying there, there's no way for me to do anything. So this is actually our conditional reaction number 7. If you see any flying segment, the best way is try to make them landing in the triangle. Landing in the triangle, put them into a triangle. If they're flying there, there's no way for you to do any calculation. right? Okay, how to make them kind of like flying from a flying segment and make them landing in a triangle? We need to kind of having the relationship, right? We need to make sure first, I need to deal with this theta. This kind of triangle must have some relationship with the theta. Second, I have these three segments, PD, QD, PQ. I must also have some relationship with the three segments. So what is the best way to put everything into one triangle? This triangle, I also have theta and also have the relationship with this PD, PQ, or QD stuff. What is the best way to make it happen? Think about it. Okay, I see a student got an idea. Yes, let's try to do a connection of BD. As long as you do a connection of BD, let's say due to the symmetric property, if I let PD equals to QB equals to PQ equals to A, this is going to be your A, right? This is going to be A over 2. Is that correct? A over 2. Hmm. In that case, this is going to be root 2, right? Because the question said, yeah, maybe we can let AB equals to 1. It doesn't matter, right? AB can be 100, can be 1 million. It doesn't matter. We just let AB equals to 1 to make our calculation a little bit easier because the question focuses on the theta's angle. I don't really care about the side. I only care about the angle. So if AB equals to 1, this is going to be root 2, right? Now, who can tell me what kind of triangle can actually have theta, can have A, and can have everything there? What is the best triangle I can do my calculation? I want to put all the segments into one triangle and then taking from there, solve the problem. I need one triangle which has a theta, which has A. Mostly, I mean, maybe I also need to have my root 2 or something, stuff like that. It doesn't matter. Yeah, I see somebody has the correct answer. Yes, it, Zihan has the correct answer. Let's try to focus on this triangle. This triangle, we'll see. Let's focus on triangle PDR. I'm going to write the triangle one more time here. PDR. So first, in this triangle, this guy equals to what? This guy equals to 45 degrees minus theta. Is that right? 45 degrees minus, yeah, it's not directly theta, but you get an idea. It's closer to theta. And PD equals to A. PR equals to A minus 2. And this guy equals to root 2. Okay, within this guy, I can actually do a cosine law. Is that correct? Because I just need a cosine law. And this guy just have exactly what I need. Do a cosine law. You have what? Cosine 45 degrees minus theta equals to a square. This will be root 2 over 2, right? Yeah, because this is 1. This is root 2 over 2, right? The entire diagonal is root 2. Yeah, root 2 over 2, right? But like I said, this is not important. right? You can put like whatever value you like. A square plus root 2 over 2 perfect square minus 8 over 2 perfect square, right? 2 times a times root 2 over 2. Is that right? Let's try to do a quick simplification. So cosine 45 degrees minus theta will just equals to 3 over 4a square, 1 over 2, a root 2. Is that right? Just do some quick calculation. Okay. Taking from here, do you still remember? We need to get what? We need to get an inequality. Your goal is try to determine theta, right? The minimum possible value of theta, ADP. So my goal is try to determine the minimum value of theta. If I want to determine the minimum value of theta, so what can I do? If I want to determine the minimum value of theta, I want to find an inequality, try to solve this, right? If I want to find an inequality, cosine 45 degrees minus theta, it actually equals to this guy. Can I build up an inequality just using this? This guy could be written as what? Is it right? Like this. This guy is more like the AMGM. Is it right? The arithmetic mean and the geometric mean will be greater or equal to what? Under root 2, 3, 4 root 2 times this guy. Do you agree with me? Differentiate to find max. No need to go for that complicated. You can just directly do an AMGM, right? No need to use the calculus. Directly use AMGM, right? Two numbers arithmetic mean is greater or equal to their geometric mean. This guy equals to root 3 over 2. Make sense? So that being said, okay, you have the cosine 45 degrees minus theta is greater or equal to root 3 over 2. So therefore means what? Means 45 degrees minus theta less or equal to 30 degrees. So theta greater or equal to 15 degree. QED. You see? Very straightforward process. You didn't really calculate too much. Is it right? We just all the way comes to here. We use a quick AMGM. We fix the problem. This is a very important thing. My solution is much straightforward than the official solution. If I give you the official solution, you can find out it actually calculates a lot more than this. It actually use it more for like the cosine law for two different angles. It used for one triangle here. Yeah, if you check the official solution, it check this big triangle, and then the second little triangle, and then replace it. You see, the first cosine law, the second cosine law, and do a lot of replacement here and there. I think it's not so straightforward. Using my solution is much more straightforward. You're directly using the AMGM. AMGM. That's really that if you use AMGM, you only use one cosine law, you solve the problem. If you can actually go back and check the official solution. In the official solution, they use the two cosine law. The two cosine law takes long calculation, but using my AMGM, you can actually solve the problem within one cosine. So far, so good? So this is what we discussed. We're trying to use the cosine law, some trigonometry, which also going to help you to solve a lot of geometry problems. So especially in this problem, we give you a lot of conditional react. Whenever you see the inequality, whenever you see the side and angle, whenever you see the flying segments. So these are all considered to be very important concepts that you need to know in order to solve the problem. So far, so good? Are we all good? All right. So if all good, let's go to our category number 3. Let's try to talk about some area-related problem. Okay? The area-related problem. If you can remember, we have talked about the first one is definition. There's nothing to say. The second one is rotation. Third one is compensation. The last one is partition. Yeah, I think we're running out of time, right? Yeah, because the first lecture, we want to give more interactions, more students. A lot of students ask for questions. It's okay. If we do not finish them today, we can leave for the next lecture. It's okay, no problem. But let me try to do as much as we could. The first one, like I said, definition, there's nothing to say. But let's try to talk something about the rotation. Rotation is always try to use the rotation, try to get the congruency. From the congruency, you'll be able to transfer your values from one side to the other. That's going to help you to solve the problem. Let's go for one example for that. Okay. Number 3, the first one is this guy. We're looking at a problem that comes from, this is like an easy problem. This is a problem that comes from 2016. Euclid question number 9. Okay. 2016 Euclid question number 9. This is a rotation problem. The question says in the diagram, ABCD is a square. Points E and F that chosen on AC so that EDF, this is 45 degrees. Okay? If AE equals to X, EF equals to Y, and FC equals to Z. Okay? Prove that Y squared equals to X squared plus Z squared. Okay? Before we jump to the calculation or something like this, so first, conditional react, number 6 or number 7, I can't remember. As long as the question asks you to do y squared equals to x squared plus z squared, what kind of thing you need? What kind of thing you need to do? This is very conspicuous. What do you need to do? This means what? Who can tell me? This is a what? Like y squared equals to x squared plus z squared. This is a what kind of thing? Who can tell me? This is a Pythagorean theorem, right? This is a Pythagorean theorem. It looks like X, Y, Z, they can form a right triangle, right? Y is the hypotenuse, and X, Z are the two sizes, right? This is a Pythagorean theorem. This is quite understandable, right? So the $1,000,000 question is, how can I create a Pythagorean theorem, right? Or like a right triangle. This is something quite understandable, right? Okay. If you want to create a right triangle, so X, Y, Z, they must be in a triangle, right? But X, Y, Z, they are not in a triangle at this moment, right? They're not in a triangle. I have to put them together in a triangle to make sure I can do all my stuffs. Does it make sense? You guys follow me? Yes or no? I need to put them in the triangle before I can do all of these discussions. So now my goal is very clear. I need to create a right triangle and I need to put XYZ into the same triangle. At this moment, you just can't because they're all together in the diagonal. How can I, my goal is, how can I move XYZ, put them together into a triangle? This is $1 million question. Okay. If you want to move a triangle, if you want to move a segment from one place to the other, the best way is try to do a rotation. How can I do a rotation? Let me try to do something like this. I'm going to try to rotate my triangle A, D, ADE versus point D to ADE. Go to CMD. What is that? I have a triangle here. I'm going to rotate my triangle all the way to here. I'm going to remove that. Remove all my lines. Rotate to here. Okay. Rotate to here. As long as I do the rotation, of course, these two triangles, they're congruent to each other, right? I just rotate to here. This is my M. Rotate to CMD. Okay? So these two triangles are similar, are congruent to each other. Let's have a quick look at it. What's going to happen for all of this? If I put them together like this, I will say this angle is the same as this angle. Is that correct? This angle is the same as this angle. So I'm going to write it here. I rotate triangle ADE to triangle DMC. Okay, if that's the case, let's have a quick observation. My angle ADE plus my angle FDC is actually equals to 45 degrees, right? Previously, this guy plus this guy equals to 45 degrees, right? Because this guy is 45, so this guy plus this guy equals to 45 degrees. Now you are telling me ADE is the same as CDM. So therefore, I can do a little bit replacement, right? ADE go to CDM. So CDM plus FDC equals to 45 degrees. CDM is here, FDC is here. Okay, so that means that this angle, FDM, equals to 45 degrees. Is that correct? Does it make sense? Yes or no? So what I'm trying to do here, let's have a quick look at it. This is 45 degrees. This is 45 degrees. Whenever you do a rotation, you know that because you rotate it, this guy is the same as this guy, right? Because you do rotation, nothing changed. If that's the case, if I do a connection, actually, my triangle EDF is actually congruent to my triangle DMF. Is that correct? I have, this is 45 degrees. So therefore, FDM is the same as EDF equals 45 degrees. DE, I'll use this color. DE is the same as DM. And DE, DF is a shared length, shared side. So this is what? A side angle side. Is that correct? So with all those information, I find triangle EFD is congruent to triangle MFD. You guys follow me? The, the black triangle and the green triangle, they are actually congruent to each other. The black one and green one, they're actually congruent to each other. Does it make sense? It makes sense, right? This is the easy one. You can actually, the black one and the green one, they're congruent to each other. As long as they're congruent to each other, if this is y, so this is y as well. Is that right? Now you find what? Let's check it out. Because first time when you do the rotation, if this is x, the x is already replaced to here, right? Your z never moved. Oh, now you actually put everything into a new triangle, this blue triangle. Oops. This blue triangle. Let me try to replace it. Yeah. In this blue triangle, you actually have x, y, z already there. Is that correct? Your goal is try to put x, y, z into a triangle, and it must be a right triangle that you'll be able to do your calculations, so on and so forth. Now, you see that? You have already put everything into a right triangle. If that's the case, if you can say this is, I mean, you already put them into a triangle. If you can prove FCM is a right triangle, you solve the problem directly. So the last question is, can you easily prove FCM is a right triangle? Yeah, I see. Zana already has the correct answer. This is actually so easy. Why? Because at the very beginning, this is 45 degrees, right? This is like the diagonal, right? You have the diagonal. This is 45 degrees. And what about this angle? I'll use the color maybe yellow. This angle is actually coming from here. This is also 45 degrees. Is that right? This 45 comes to here. So obviously, this is actually a 90 degree. I would just say that obviously, triangle FCM is a right triangle with angle FCM equals to 90 degrees, right? This is a very obvious calculation, right? You don't really have to do too much proving. You can see that. So therefore, within triangle FCM, we can use the Pythagorean theorem. You have y squared equals to x squared plus z squared. Y squared, y is here, z is here, x is here. So QED. You see, this is actually a very easy peasy process. Understandable, right? Easy peasy, understand the process. So the most important thing for rotation is try to make sure that you can rotate from one side to the other, transferring the segments, the angles into another shape, and then moving forward, you'll be able to do the calculation. This is one of the most important things. Okay? So having a good understanding to this part is actually very important. That's going to help you to transfer the shape from one side to the other and then wrapping up this calculation process. Okay? So this is our first very important strategy, rotation. We still have two more very important strategies, compensation and partition. I think we can save it to the next lecture because we can use the 3 lectures cover all those, geometry related stuff. So we still have some time. All right, I think that wraps up our first lecture. So let's have a quick recap. The first lecture we focus on the 2D geometry. especially focus on the triangle, quadrilateral, polygon, so on and so forth. We use some of the Euclid question number 8, number 9 questions. We don't want to do the easy ones. The first couple of questions are so easy, right? So for this lecture, we focus on some relatively difficult problems, but still we want to give you guys more idea, right? How to do all those problems. So by giving you all those problems, you get an idea, right? How to see the major problem, the major categories, right? Using either the similarities or using the areas or use the trigonometries. So hopefully we give you guys a big direction how to solve the problem. So moving forward, the next step is that we're gonna assign we're gonna release the assignment. Every lecture we have assignment. You have 1 week to finish all those problems, and the teacher is gonna help you to mark it, give you the feedback. And the next lecture, we're gonna review the assignment and moving forward to the next topics. All right, I think that wraps up our today's lecture. Like I said, we don't want to go over time too much. We have to respect our time. And the first lecture, because we have more students asking for questions, but normally speaking, our regular lecture, we will not go for our scheduled time. And yeah, I think that's pretty much what I want to say for today's lecture. You have any questions? All good? Okay, thank you guys for joining us for today's lecture. I wish you guys a good weekend, and maybe I'll see some of you guys around in the following lectures. And for the students, for the next lecture, we're going to go to our official lectures. Please change your Zoom ID. We'll use our regular Zoom ID. This one is only for the first time. Thank you, guys. Yeah, you can scan for this little our assistant if you want to have some free lectures. All right. Thank you, guys. Have a good one. Bye.